Section: Introduction. In this section, we introduce continuous concept mixing, or co-mix, a framework that enhances next token prediction by incorporating continuous concepts. We begin by outlining our problem setup and the process of extracting concepts using a sparse autoencoder, say. Next, we explain how we select these concepts and how the model integrates them into its hidden state to improve language modeling. For our problem setup, we focus on a language modeling task involving a vocabulary and a training dataset. We utilize a pre-trained language model for concept extraction, which predicts the probability of the next token based on previous tokens. We extract continuous concepts from the model's hidden state, aiming to train the model to maintain the same autoregressive structure while incorporating these concepts. To extract high-level concepts, we employ an SAE, which transforms the input into a high-dimensional sparse activation to reconstruct the original input. When applied to a large language model, the SAE breaks down the hidden state into various dimensions, each representing a distinct, semantically meaningful concept. We specifically use a top KSAE, which enforces sparsity by keeping only the largest entries in the activation. The SAE consists of a linear encoder and decoder, where the encoder maps the hidden state to a concept space, and the decoder reconstructs the hidden state from these concepts. We train the SAE by minimizing the reconstruction loss, which helps isolate the most important dimensions that explain the model's features. Each activated element in the concept vector is interpreted as a meaningful concept. Section Summary. In this section, we introduce continuous concept mixing, co-mix, a framework that enhances next token prediction by integrating continuous concepts extracted from a pre-trained sparse autoencoder, say. By interleaving these concepts into the model's hidden states, we aim to improve language modeling and enable better interpretability and control during text generation. Section: Continuous concept mixing. In this section, we describe the main training process of co-mix, which includes a framework for selecting concepts and 2 training steps to learn and apply continuous concepts. First, we identify important concepts using an attribution score that indicates how much each concept affects the output. Next, we predict these selected concepts from the model's hidden state using a cross-entropy loss, helping the model learn which concepts to represent in its hidden layers. Finally, we use the predicted concepts to form a continuous concept that is mixed into the hidden states, allowing the model to learn how to use both the continuous concepts and the token hidden states effectively. For selecting target concepts, we note that while the extracted concept represents key features of the current input, it doesn't necessarily show which concepts are most relevant for predicting the next token. To address this, we use attribution, which measures the impact of each concept on the output. Specifically, we calculate the attribution score by multiplying the loss gradient with the input. This score helps us identify significant concepts to include in our language modeling. When predicting the selected concepts, we first identify the indices of the concepts with high attribution scores and use these as labels for prediction. We then learn to predict these labels using a linear model that outputs logits by minimizing the cross-entropy loss. To help the model better internalize the concepts, we mix the predicted concepts with the existing token representations. We compress the predicted concepts into a compact vector, referred to as a continuous concept, which we then interleave with the token vectors. This compressed vector is added to the model's hidden sequence, which is processed by the remaining transformer blocks. This design not only enhances the model's performance but also provides interpretability and control, allowing us to analyze and adjust the predicted concepts during generation. Our training objective combines the standard next token prediction loss with the concept prediction term, using a tunable coefficient to balance the two. Section Summary. In this section, we describe the co-mix training pipeline, which involves selecting important concepts based on attribution scores and predicting these concepts from the model's hidden states to create continuous concepts that are interleaved with token representations. This approach enhances the model's ability to learn useful concepts for token prediction while also improving interpretability and controllability during the generation process. Section: Experiments. In this section, we provide an empirical evaluation of Co-Co mix by exploring several key questions. We aim to determine if Co-Co mix enhances next token prediction during LLM pretraining, if it performs better in weak to strong supervision compared to other knowledge distillation methods, if it offers model interpretability and steerability, and how each component of Co-Co mix contributes to overall performance. Before addressing these questions, we outline our experimental protocol. For our training setup, we utilize a pre-trained open-source model based on GPT-2, specifically the 124 million parameter version. We experiment with Co-Co mix using 3 different active parameter counts: 68 million, 386 million, and 1.38 billion, all with a context length of 1024. Our analysis primarily focuses on the 68 million model. It's important to note that the active parameter count includes those in the new layer, while for other baselines, we match this count by adjusting the hidden state size. Co-Co mix requires fewer floating point operations than the pause token but more than the next token prediction method due to the integration of continuous concepts. We use the open web text dataset for pre-training, ensuring consistency with the distribution used for our model. Most experiments involve 20 billion training tokens, except for the main experiment, which uses 200 billion tokens. In terms of baselines, we consider the standard next token prediction procedure and the widely used knowledge distillation method. We exclude knowledge distillation baselines that require multiple teacher models. For knowledge distillation, we minimize the difference between the outputs of the teacher and student models while balancing this with the next token prediction loss. We do not generate synthetic datasets for distillation due to inefficiency. For evaluation, we assess validation perplexity on the pre-training dataset and 7 downstream tasks that test common sense reasoning and reading comprehension. These tasks include Lombada, Wikitext 103, Hella Swag, PIQA, Social IQA, Arc Easy, and Wino Grande. We also use Open Web Math as a pre-training dataset to show that concepts learned from a pre-trained model can be applied to Co-Co mix, even if trained on a different corpus. Our main results highlight 2 key findings. First, we compare Co-Co mix with next token prediction in a large-scale pre-training setup, and second, we compare it with knowledge distillation, particularly in weak to strong supervision scenarios. When applying Co-Co mix to next token prediction, we find that it significantly enhances performance across various downstream tasks, especially when trained on 200 billion tokens. Our results indicate that larger models benefit from concepts extracted from a smaller model, demonstrating effective weak to strong supervision. Co-Co mix also shows improved performance over next token prediction while using fewer tokens, indicating high sample efficiency. Notably, the performance gains from Co-Co mix increase with training steps, showcasing strong generalization. In our comparison with knowledge distillation, we observe that Co-Co mix outperforms it across multiple scenarios, including when a stronger teacher model instructs a smaller student model, in weak to strong supervision, and when there is a distribution shift. Co-Co mix shows significant improvements, particularly in weak to strong supervision, where it enhances average perplexity while knowledge distillation does not yield substantial gains. This is likely because a weaker teacher may provide noisy or suboptimal knowledge. We also see that models trained with knowledge distillation tend to lag behind standard training as the student model surpasses the teacher, especially in distribution shift scenarios. In contrast, Co-Co mix effectively utilizes valuable concepts, leading to consistent performance improvements. Section Summary. In this section, we empirically evaluate Co-Co mix by examining its impact on next token prediction performance, its advantages in weak to strong supervision compared to knowledge distillation, and its contributions to model interpretability. Our results show that Co-Co mix significantly enhances performance across various model sizes and tasks, demonstrating high sample efficiency and consistent gains over traditional methods. Section: Interpretability and steerability of Co-Co mix. In this section, we discuss the interpretability and steerability of Co-Co mix. One of the main benefits of CoCoMix is that we can understand how it works and guide its outputs. As the model learns to predict concepts in its hidden state, we can see which concepts it emphasizes by looking at these predictions. By increasing the strength of a predicted concept, we can influence what the model generates. For instance, we multiply the predicted concept by values between -10 and 10. To test this steerability, we adjust the activation of the same concept in the pre-trained model's latent space and check if the output reflects that concept. We used a model with 386 million parameters, trained with CoCoMix, based on GPT-2. Our results show that when we amplify the concept related to website address, both models generate actual website addresses, indicating that our model has effectively learned the concepts aligned with GPT-2. More examples of this steering can be found in the appendix. Next, we analyze CoCoMix's effectiveness. We use a model with 69 million parameters trained on 20 billion tokens from the Open Web Text dataset. We first examine whether the attribution score successfully identifies important concepts. We trained CoCoMix using the activation value for concept extraction instead of the attribution score. We found that the activation value also reflects the importance of the concept well. However, using attribution scores significantly improved performance, increasing sample efficiency by 17.5% compared to using activation values alone. We believe exploring other selection criteria could enhance CoCoMix's performance or help eliminate undesirable concepts, such as unsafe ones. We then compare CoCoMix with direct hidden state prediction strategies, where we predict the full hidden state without projecting into the concept space. To ensure a fair comparison, we replaced the concept prediction head with a two-layer multi-layer perceptron that predicts the hidden state directly. Our findings show that direct hidden state prediction leads to a drop in performance, likely because SE can break down the latent space into meaningful concepts, while predicting all hidden states may introduce noise. We also analyze the weights of the compression layer to see how CoCoMix uses the predicted concepts. We visualized the weights for each concept and found that some weights are close to zero, indicating that CoCoMix learns to ignore less useful concepts. This process likely allows CoCoMix to effectively supervise learning by disregarding ineffective concepts from a weaker model. In our component analysis, we evaluate the contributions of each part of our method: concept prediction and concept insertion. Our results show that both components are essential for improving performance. Using concept prediction alone leads to a slight reduction in perplexity, but adding concept insertion significantly enhances effectiveness, demonstrating its importance in leveraging the pre-trained model's reasoning. We explored two methods for integrating the continuous concept into the model's hidden state: insertion and intervention. Insertion places the continuous concept before the token embedding, while intervention modifies the hidden state directly. Both methods improve pre-training performance, but insertion performs better, allowing the model to recognize and utilize concepts more effectively during generation. Lastly, we compare CoCoMix with a baseline that uses pause tokens, which are additional learnable tokens that help the model think before predicting the next token. We found that CoCoMix consistently outperforms the pause token, showing that our continuous concept insertion provides valuable information that enhances performance. Section Summary. In this section, we demonstrate that CoCoMix enhances interpretability and steerability by allowing us to control model outputs through concept amplification, confirming its effectiveness with a pre-trained GPT-2 model. We also analyze the contributions of various components, showing that both concept prediction and insertion are crucial for performance improvement, with our method outperforming alternatives like pause tokens. Section: Related Work. In this section, we discuss related work that goes beyond traditional token-level guidance in language modeling. While predicting the next token is the usual approach, recent methods have started to explore guidance that extends beyond just language tokens. For example, some techniques focus on better targets, like using multiple token predictions to understand long context dependencies or predicting sequence embeddings. Others introduce new input types, such as latent variables or self-generated thoughts, which have improved reasoning abilities. Recently, there has also been interest in concept-level modeling using local encoder-decoder architectures to represent language at a higher level of abstraction. Some methods add extra tokens to the input to enhance computation during inference. In contrast to these approaches, we propose a pre-training method that combines next token prediction with continuous concepts, linking high-level ideas with detailed token guidance. We also explore sparse autoencoders, SAEs, which enhance traditional autoencoders by adding sparsity constraints in the latent space. The features learned through SAEs are often interpretable and distinct, making them valuable in various fields, including language modeling. SAEs have gained traction in mechanistic interpretability because they can capture coherent semantic concepts, aiding in the identification and manipulation of these concepts for controlled model outputs. Among the SAE variants, top K SAEs apply explicit sparsity using a top K activation function, proving effective even in large models. In our work, we utilize SAEs and, to our knowledge, are the first to apply them to the pre-training of large language models, achieving strong performance while improving the interpretability and controllability of the model. We also relate our method to knowledge distillation, KD, which involves transferring knowledge from a teacher model to a student model to boost performance. Co-mix extracts high-level semantic features from a pre-trained model to train a base model. Recently, KD for large language models has gained attention, as it uses knowledge from a teacher to enhance the generative and encoding abilities of a student. However, applying KD in LLM pretraining is challenging due to the enormous scale of tokens, which can reach billions or trillions. This often leads current methods to rely on simple token-level probability matching. Additionally, while pre-trained models hold a wealth of learned information, reusing knowledge from smaller teacher models can be difficult. In our work, we demonstrate that co-mix can leverage concepts extracted from smaller models to train a larger model, showcasing weak to strong supervision.